Hi, just a quick update on this iPod Nano installation. Hopefully we should have production boards in next week, so I'm just doing a bit of testing. The installation consists of 70 vertical strips. Now this is one vertical, just laid out on the bench. I've just folded it with a piece of cable because my bench isn't long enough. But there's basically 5 of these boards, each board having 8 screens, and they'll be in one long vertical strip. At the top there's a connector board that transitions these little 2mm connectors into a ribbon cable. The main reason for using ribbon just simply is it's easy to make the cables up. And bottom end there's a mechanical piece that's also got a termination resistor. And this ribbon cable comes out of one of these data and power splitter boards, which I'll go into in a minute. And that's then in turn driven from one of these 4-port EasySync USB high speed to quad 485 boards with just a breakout board that I've stuck on the middle to send 4 lots of 485 down a single Cat5. This board does a few things. There's a total of 70 of these vertical strips in the installation. Obviously we don't really want to have 70 RS485 buses because that would be ridiculous. So each of these boards drives 5 units, and because we're driving quite a large number of loads, there's 40 receivers per segment, we're actually having to split that and provide a buffer for each segment. So each of these 5 connectors drives one strip, and we've got a big polyfuse to protect the cabling against the power supply. There's an RS485 driver, which is, again, has got its own protection. There's a couple of Xenas and a couple of polyfuses to protect the Xenas against shorts between the data lines and the 24-volt supply, which can happen because of these little 2mm connectors. If these get mated offset, then we can quite plausibly have 24 volts going up the data line, so we don't want that to cause any damage. There's a little bit of power management going on here. There's a 12-volt switching regulator. That is to provide power because we may need some small fans for cooling locally, so there's a 12-volt fan supply, and then there's from that we get the 5-volt supply for this buffering stuff. The receiver, this is actually quite a neat device. I've used it a few times. It's from a company called NVE, and it's a magnetic isolator that has a completely passive input stage. So basically the front end of this is basically a coil. So this means it needs no ground referencing, which firstly means you don't need any ground, so you don't need to use an isolated box at the other end to avoid any ground loop effects. But also means just on a more simple level you can get 4 complete buses down a single Cat5 because you don't need that ground return. One disadvantage of this is it's basically one way, so we're only sending data out to these. Although technically these boards do have a data return path, we're actually not using that. One problem with RS485, trying to buffer that bidirectionally, is deciding which side is transmitting at any given time and enabling the driver in the right direction. Now, in principle we could have done this, but this splitter would basically have had to have knowledge of the command protocol and actually decoded the data, worked out the direction from that, and decided which of these sort of 5 buffers to enable the data back from. So basically pretty much the only thing we need data back for is when we're programming the flash, because we've got an unpredictable read time. But because we're going to be programming different content into each of these displays, and there's going to be 160 displays on each bus, in practice what we can do is we can send sort of a block of basically the onboard processor handles some of the programming arrays, so we send a 4K chunk of data, and the processor there sits programming and then erasing as required to program that data in, which can take up to sort of 100 milliseconds or so. But because we're programming so many, what we can do is we can send a block to each one in turn, and then by the time we've got back to the first one, we know that erase time is going to happen purely because of the amount of time it takes to send all that 4K of data to all 160 nodes. So we don't really need that return path, so we can simplify our data into basically a one-way stream. So our splitter is literally just a dumb splitter. It's a receiver, and then it just sends that same data out in parallel over 5 different buses, which just makes life a bit easier, and it's fewer things to go wrong, fewer things where whenever you've got something in the middle having to handle the data, it's yet another thing that if you have problems, it can be a real nightmare to debug, to actually figure out exactly where the problem's happening if you've got some data getting lost somewhere along the line. So having this as just a dumb buffer just eliminates one possible source of problems. Now, a while ago I did a video on using PCBs as front panels for making sort of quite nice looking low volume things without the tooling of printed and cut front panels. This splitter, we're originally going to put it in this DIN rail housing, so it could either be clipped to a DIN rail or panel mounted, but as it turned out we were a bit short on depth. So what I ended up doing was doing this so that we've got all the connectors on one side, all the other stuff surface mount on the other side, and I've just got some frames cut from, this is 3.2mm PCB material, and a rear cover, and this thing isn't going to be seen, this is going to be hiding in a cable trough, but obviously you need protection for those components, they don't get bashed when it's being installed. So this just formed a simple sandwich casing, so everything's nice and protected, but it's nice and thin. We've also got these feet on it because this is going to be sitting in a cable trough, and there's going to be cable sitting on the bottom, so having these feet means this thing can actually sit on the bottom of the trough but without having to mess about moving the cables either side of it, and there's a couple of holes there in case you want to cable tie the data. So basically 4 of these sit on one Cat5 cable, and the way the data is basically tapped off for each unit is that the pairs effectively step over from in to out, so the data comes in on 4 pairs, it takes 1 pair off to drive this board, and then it steps the remaining 3 across by 1 set, so that the next one that's plugged in line goes on the next pair. So all it needs to do is just plug all these, 4 of these in a chain, and then each one will take data from its pair in the incoming Cat5 cable, so we don't have to, for example, have any addressing or any selection on here. So again, it just keeps the installation nice and simple, and it means that, for example, if one of these needs to be replaced, we just unplug it and plug another one in, and there's no addressing to set up, so that keeps things nice and simple. There's a slight fail on the legend here, because at a fairly late stage I decided this thing needed to go the other way up, and when I rotated all the text I forgot to recenter that, because I was looking at it from this side of the PCB, so it was a bit hard to see, but never mind, no one's going to see it, so not too big a problem. Now, because we want to keep this thing low profile, I wanted to use horizontal sockets, so we've got horizontal entry, Cat5s, and horizontal power connector in there. One thing I really struggled with, obviously these, I'm using shielded Cat5s purely because we've got a solder tab to actually solder them down so they're nice and solid, and obviously it needs to be the type that actually has the tab on the top side, because otherwise you wouldn't be able to release it by getting on the bottom side. And I really had trouble finding a Cat5 connector with tab up that didn't have these shielding things. So obviously if you're using it like this, these things are a pain in the ass because they'll get caught. And I ended up using one by, I think, Stewart, which is quite expensive. I was really surprised how hard it was to find just, one of these without the shielding lugs. Bit of a real pain, but found it in the end, and so I just had to pay, I think it was about £2 each or something ridiculous. There's a couple of status indicators. There's a power on and a data light that just flashes. It's actually just connected to the output of the 485 receiver. These actually use through board LEDs, so these are actually LEDs that are designed to mount upside down and shine through a hole in the PCB. It's always handy just to have these little diagnostics when you're sort of trying to debug a big installation. Now, a few people asked about how the IDs work on this system after my last video. What happens is we've got an RS485 bus that's connected to all these units in parallel. There's also a single data line that goes from one to the next in a chain, and basically what happens is when each thing boots up, it looks at the level of that line. Now if it's high, above fairly close to 3 volts, it assumes that it's connected to the previous one, and at the beginning of the chain there's actually a resistor to ground, so on each of these channels there's one resistor which is a different value for each channel, and there's a pull-up resistor on the input. So if it sees anything below sort of hard pull-up, it says, oh okay, I'm the first one, I'm the one right at the top of the chain, measures the value of that resistor, and depending on the value of that resistor will group itself as to start, it'll either be 1, 41, 81, 121 or 161. And when it's figured that out, it then sends a serial byte down the chain, so each one receives that, says okay, for example, if this one was 41, then it will send 42 down here. This is say, it would receive that byte through a UART and say okay, I'm 42, and then forward 43 down. So the whole string will basically address itself. One major issue with big installations like this is you don't really want to be messing around having to program IDs on individual things. You're in a fairly sort of stressful install situation. If you've got a problem, you want to just swap a board out and not worry about it. So this system, just handles all those IDs. As long as you plug the right ribbon cable into the right connector, the entire string will have its correct ID. So that's quite a neat system for dealing with that sort of situation. I mentioned the termination resistor at the bottom, and I've got quite a good illustration of here why that's important. See what happens if I disconnect it. Now what I'm doing, I'm actually, instead of reading from flash, which I was doing earlier, I'm actually sending the data directly, so we're sending a lot of data and we can easily see any corruption. But what's happening is the corruption is actually happening at the beginning of the chain, not at the end. So all the ones further down are still working fine, but it's only the ones which are near the beginning of the chain. In fact, as you get near the beginning of the chain, it actually gets worse. So what's going on there? Right, to understand what's going on here, we need to look at the scope. So the top waveform, this is one of the two RS485 lines as it's fed in at the top of the chain, and this is what it's like when it comes out the bottom. Now I've actually set the grid up so that one grid division represents the delay between the top and the bottom. So yeah, this 485 bus acts like a transmission line, so we get a delay along it of about 110 nanoseconds. So what we can see here, we've got the signal going in, and then we can see this bounce here. Now what's happening if I disconnect the termination? Two things happen. The amplitude of this increases a little bit because the termination acts as a load, so there's just a resistive effect. But we see this bump here gets much more pronounced. What this actually is, this is actually a reflection. So our signal goes in, reaches the bottom, and then it starts bouncing back up the line. And if we look at the delay from start to the end, and then the same amount of delay, that's where we're seeing this big hump here. So without the termination, the signal reflects off that open end, and then by the time it gets to here, it's basically adding to the signal that's being sent to produce this peak. And this can cause all sorts of problems with the actual overall signal. It's trying to establish a sort of sensible level to slice this to get a recover the data. But if you've got this massive, great sort of shark fin on top of it, then that's going to ruin your day. So if I turn what happens is by turning the termination on, it's absorbing some of that spike at the end of the line and significantly reducing the amplitude of this in proportion to the overall signal. And in fact, without the termination, you can actually see there's actually a third bounce. So it goes from the beginning to the end. Then this is the bounce at the beginning, and then we've got this peak here, which is it bouncing yet again down to the far end. So and obviously because this bounce time is of a similar order to our data bit time, if that reflection comes in roughly when we've got a bit transition, then that's going to send out all our signal lines haywire. So once you get up to systems that have got either a fairly long cable length or quite a lot of, because we've got these PCB traces or where we've got sort of long PCB traces, these obviously zigzagging around here and also around the edge of the PCB. We've got the distributed load of the RS485 receivers providing some sort of capacitive load. Then pieces of wire start acting as sort of series inductors, and you get all sorts of interesting effects. So while in quite a lot of situations you can ignore termination, there are certain situations where it can actually be quite important, to the point where the thing will actually stop working if it's not terminated properly. And yes folks, there are a couple of minor little fails on this board layout, and that one was me not really reading the microchip data sheet. This is a MCP 16301 buck converter, which I use all the time, but I almost always use it for 5 volts. But when you're outputting more than 5 volts, you actually need a Zener in there to avoid the voltage smoking the chip, basically. So that was a little error and a minor pinout fail on this converter. I actually cross-checked this PCB against another PCB. I then remembered that other PCB was also wrong, but the other one I didn't actually need to fix because I could just swap the wires around at the far end. So fortunately there's only 14 of these, so it's not a big deal to fix that. But this is all working, so hopefully we should be aiming to do a follow-up test of this in the next few days, which should be quite fun if we can find the space to do it.